So determining a chemical formula from experimental data. This is a little bit backwards of the percent composition. So we can find an empirical formula from elemental analysis. So you could take the compound and decompose it into elements, or you can measure the masses of the elements that react to form the compound. And so sometimes you'll have masses given that way, or sometimes you'll get the percent composition. So it's important to remember that the empirical formula is a ratio of atoms. It's not masses. And so we have to get to particles in here. So here are the steps for finding an empirical formula. You start with the masses of each element. Sometimes you're just given it. They give you this mass and that mass, great. Sometimes they give you percentages. So to make the percentage into a mass, just say, well, what if I had 100 grams of the compound? They said it's 75% iron. If I have 100 grams, then I have 75 grams of iron. So you can just take the percent sign and change it into a G, and you've got your masses. Then you convert those masses to moles using the molar mass. And then we need to find the smallest whole number ratio. So we'll take the moles of each element and divide by the one that's the smallest. Sometimes we get whole numbers. Great, those are the subscripts. Other times, they're not. So this is my personal guideline. And since you're in my class, this would be a good thing to go by. If the numbers you're getting there are within 0.2 of a whole number, you can round it to a whole number. So what do I mean by that? If you get 1.83 when you get the ratio, you can round that to 2. What if I get 1.78? Can I round that to 2? No. Because that's more than 0.2 away from the nearest whole number, okay? If I had 2.25, can I round that to 2? No. If I have 2.19, can I round it to 2? Yes. That's just my guideline, okay?
If it was 2.23, would you round it to?
If it's 2.23, it's more than 0.2. So if it's 2.20 or larger, don't round it. Usually we don't get into things that are that picky. It's usually more obvious. But that's just a guideline. So because sometimes students just want to round everything, and this is a place where you can't do that and get the correct answer. What if you can't round it? Well, then you need to multiply all the subscripts by the same small whole number. So there are those decimals are fractional equivalents, right? 0.5 is the same as 1/2. If you multiply something that ends in 0.5 by 2, you're going to get a whole number. So if you understand the fractional equivalence, you can just pick the number and be done with it. A lot of students are like, what the heck are you talking about? Okay, there's also a really good trial and error method. Multiply it by 2. Did that get you within 0.2 of a whole number? No? Try 3. Try 4. Try 5. Usually you don't have to go past 3. So those are the instructions. Let's play the game. Sample compound is decomposed in the laboratory, produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula. So here I'm given masses of each element. That's what I have to start with. I convert the masses to moles, and then I'm looking for ratios of moles. So 165 grams of carbon. Well, I'm going to convert that to moles. And the conversion is the molar mass from the periodic table. So 165 divided by 12.01, 13.7. So this is a place where in your final answer, you're going to have whole numbers, no sig figs. But if you round too much in the middle here, you're going to get the wrong answer. So keep more digits than you think you're going to need. So minimum by sig figs would be 3. I'm definitely going to keep my 2 extras. So that's moles of carbon. I have 27.8 grams of hydrogen. I'm going to convert that to moles. 1 mole of hydrogen per 1.008 grams of hydrogen. .579 moles. Bless you. And 220.2 grams of oxygen. And I'm going to convert that to moles. So 220.2 divided by 16. 13.76. What the heck? Just I'm going to put all of them. I took the masses of the elements and I converted them to moles. So these numbers, I can't say, well, the formula is C14 H₂O14. I can't just round those. I want the lowest, the smallest whole number ratio. So I'm going to pick the smallest of those numbers, which happens to be the carbon, 13.738. I'm going to divide everything by the smallest. So I'm going to divide this one by itself. So that one always comes out to be exactly 1. I'm going to divide this one by 13.738. So 27.579 divided by 13.738, 2.007. Oh, that looks like a whole number. And divide this one. Now you might say, well, that's going to be 1. Divide it anyway, because sometimes it ends up being something that you don't expect. So those numbers, 2.007 and 1.0017, are both close enough to a whole number that I can round them. Right. If this was, 2.207, I shouldn't round it. If it was 2.2, I could round it, but not anything more.
I'm saying, just say 2.2?
We'll look at there's an example coming up that'll show us what to do with that. So I can round this to 2, and I can round this to 1. Those are the subscripts in the formula. How do you know which element to put first? Do it in the same order that the problem gave you. They kind of just naturally do that, and it ends up being right. So they gave me carbon first, so I'm going to list carbon first. So C, I'm not going to write the 1 because I'm a chemist. I don't write 1s. But I understand there's a 1 there. H, 2, and O. Yes? Pretty much, yeah. So this is not a compound that we learned how to name, right? This is an organic compound, and so that just is way too complicated. You don't want to hear about it.
Just a compound we created an experiment, and we're just trying to.
Yeah, you're learning the process of finding an empirical formula. And organic compounds give us much more interesting empirical formulas than some of the other ones. So that's why a lot of the examples will have them. But yeah, just do the same order.
Basically, it's saying for every basically every 2 hydrogen atoms, there's 1 carbon and 1 oxygen.
Yes. Yep.
So it's just basically showing the molecule.
Yeah, it's the ratio of atoms in one molecule, or the ratio of moles of those atoms in the compound. It's ratios of particles. Yes. Could you call it carbon water? Well, you could, but it's not the name of it.
What's the name?
Well, it's probably formic acid. Formic acid?
Because that's just empirical.
No, I'm sorry, it's not formic acid. Formaldehyde? Formaldehyde. Yeah. Let's do this one. Ibuprofen again. I didn't pick it, the book picked it. Now, there's a previous problem that gives us the formula for ibuprofen, but the process is what's important here. What's the empirical formula for ibuprofen? Let me just... Okay, so here we're given percentages instead of masses. But if I had 100 grams, then 75 grams, 75.69 grams would be carbon, and 8.8 grams would be hydrogen, and 15.51 grams would be oxygen. The formula is going to be the same. It's just easier if I pick 100 grams. Okay? So I have 75.69 grams of carbon. And we're just going to convert it to moles again. Yeah, this guy, this engineer is just really blowing his horn, literally.
Basically, it's just
I live in Reedley, and there's train tracks that go through the middle of town. And the train usually comes at like 3 a.m. And they are legally required to sound their horn at every intersection. But they're not required to sound it for 15 seconds at every intersection. And so then when people complain, they do it more. So we learn just to shut up about it. It's really pretty ridiculous, though. I suppose that is one of the benefits of being the engineer, is you get to make that loud noise.
If you have percentages like that, they would all equal up to 100. Could you just, instead of finding it like that, could you just all subtract it by 100? That work for that?
Well,
finding oxygen, if you already had it at 2.
yeah, if they gave you these two and they didn't tell you about the oxygen, they just said oxygen was there, yeah, you could subtract from 100 to find it. Okay. Anybody check me? Did I do it correctly? Okay. So I got these weird numbers. What do I do next? Divide by the smallest. Okay. The hardest thing about doing these problems is not the individual steps. It's remembering, what am I supposed to do next? So I'm going to divide by the smallest. And that one, you're always going to get one that's 1. So this one, .7301 divided by 0.969375. And so, we don't want to do any mental math in our, say, well, that's almost 1 and 8.73 divided by almost 1 is the same thing. Well, no, not quite, because it's not exactly 1. And so this one comes out to be 6.501. Can I round 6.5 up to 7? No. I'm going to multiply by 2. If I take this number and multiply by 2, try it, times 2, I get 13.002. Is that close enough to round? Yes, it is. So this is 13. The ratio is 6.5 to 9 to 1. I need to keep the same ratio. So if I multiply 1, I have to multiply all the others by the same number. So this is times 2. And, you can do that. 18.0118. Close enough to round to 18. And the last one, 1 times 2 is 2. So these are my subscripts. I've got C13, H18, O2. Yes?
What happens if the number you multiply with still has to be multiplied and you keep multiplying it?
What if this one doesn't come out to be a whole number?
Yes.
Then go back and try 3.
Okay.
And if that doesn't work, try 4. Now, if you do it to one of these and you get if you do it to the problem one and you get a whole number, and you go to one of the others and do the same thing, and now you've got something messed up, there's probably something wrong with the problem. That shouldn't happen. Yeah. So any questions? I multiplied by 2 because 6.5 is not close enough to a whole number. I need this to be a whole number.
Is it going to always be carbon, hydrogen, and oxygen?
No, it will not always be carbon, hydrogen, and oxygen. It often will, but not always. Excellent question. Anybody else? Okay, so that's an empirical formula. The molecular formula tells how many.
So what they just said right there about that it's not always going to be CH, would acetate be an example?
Well, acetate would also be carbon, hydrogen, and oxygen. We're going to do problems like this with other elements. It's not always just going to be those. Okay, so the molecular formula is a multiple of the empirical formula. To find the molecular formula, we need another piece of information, and that is the molar mass of the compound. So they have to give you that, because we're not going to do mass spectrometry or anything else where we're finding the molar mass of a compound. So it's going to be given to you in the problem. And the molecular formula is the empirical formula that we just learned how to figure out times some number. How do you find out what that n is? You take the actual molar mass, this is given to you, and you divide by the empirical formula mass. So the formula you found, calculate the molar mass of it. And divide that into the actual molar mass. You'll always get a whole number here. So we'll do an example. A compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? So they already did find the empirical formula. So the molecular formula is CH times something. We know that the actual formula weighs 78.11 grams. So we're going to take 78.11 grams per mole, and we're going to divide by the mass of our empirical formula, which is 12.01 plus 1.008. And my calculator is giving me 6.0001. Which is 6. I'm trying to find out how many of these are in the whole formula. There's 6 of them. So we can think of this as CH, there's 6 of them. But that's not how we write the formula. This number that we just calculated is going to multiply any of the subscripts in the empirical formula, and so this is C6, H6, which is benzene, if you're curious. Any questions? If you can see the idea of what we're doing here, it's a lot easier to remember how to do it later. If you're learning steps, just rote memory, you can still do it successfully, but it's going to be harder because you don't really understand what you're doing. So we're trying to find out how many of these fit into the actual formula. I'm given the mass of the actual formula. I can calculate the mass of this. So to find out how many of these are in this, I divide. Okay, so combustion analysis is one way to find out what the empirical formula for a compound is. You take this compound and you weigh a certain amount of it, and then you burn it, and you measure what's given off. And for these problems, it will be carbon and hydrogen or carbon, hydrogen, and oxygen, because those are the kinds of compounds that this analysis works for. So if we know the mass of the product and the composition of the elements in those products, we can figure out the mass of element that was in the original compound. So in combustion, all of the carbon becomes carbon dioxide. All of the hydrogen becomes water. The original mass of oxygen has to be found by subtraction, because in order for this to burn, we're pumping a whole bunch of oxygen into this. And so we can't just say, oh, well, the oxygen is what was present in these products. That's not true. So here's a picture. So here's a little furnace. You weigh your sample and you stick it in here, and you pass oxygen over here because oxygen is necessary for combustion, and you ignite this so it burns, and when it burns, all the carbon becomes carbon dioxide, all the hydrogen combines with oxygen to form water, and we're sending the products out through these tubes, and this first tube has a water absorber in it. So we weigh this tube before the analysis, and then we weigh the tube afterwards, and it's heavier because the compound in there soaked up all the water that was given off. It's kind of funny to think of water being given off when you're burning something, right? If you hold something cool above a gas flame until it warms up, you'll initially see a little bit of condensation on it because the water in the combustion gases condenses on that colder item. So after it goes through here, it's going to go through another tube, and this contains a different compound that will absorb all the CO2. So again, you weigh the tube before and after, and you can find out how much CO2 was given off. Questions about the process? I'm not going to test you on, I'm not going to make you draw this diagram or anything, but it's helpful. We have to be able to do the problems, and if we understand how the combustion analysis is done, it makes more sense. So, upon combustion, a compound containing only carbon and hydrogen, there's no oxygen in this one, produce 1.6 grams of CO2 and 0.819 grams of water. Find the empirical formula. So this is find the empirical formula, which you did in Chem 3A. This is taking it another step. So I've got 1.60 grams of CO2. I need to find out how many moles of carbon I've got. Well, I can take grams of carbon dioxide and I can convert that to moles of carbon dioxide using the molar mass of carbon dioxide. So down here for CO2, 12.01 plus 2 times 16. So 1 mole of carbon dioxide weighs 44.01 grams. But what I want is moles of carbon, right? How many moles of carbon are in 1 mole of CO2? 1. This comes from the formula, right? CO2 has 1 carbon and 2 oxygens. 1 mole of it has 1 mole of carbon and 2 moles of oxygen. We don't care about the oxygen. We care about the carbon. Now, I could take my moles of carbon and calculate the grams of carbon to be at the beginning of my other procedure, but then I'm going to take grams of carbon and convert it to moles of carbon, so maybe I could just stop here. Moles of carbon. So 0.0363. My starting number had 3 significant figures. I definitely don't want to go any fewer than that. Moles of carbon. And then I've got 0.819 grams of water. So I'm going to convert that to moles of water. And then I don't want moles of water, I want moles of hydrogen. So in 1 mole of water, how many moles of hydrogen? 2. From the formula, H₂O. So 0.819 divided by 18.016 times 2. So that's a good question. Why am I ignoring the oxygen? So the oxygen in these products did not come from my original compound. My original compound only had carbon and hydrogen in it. The oxygen came from the oxygen gas that I poured into the furnace so that the thing would burn. So I don't care about the oxygen. I'm only looking at the carbon and the hydrogen. All of the carbon in that CO2 came from the compound burning. All of the hydrogen came from the compound burning. The oxygen, in this case, just came from the oxygen that we added later. Okay, so this is how we get the moles of carbon and moles of hydrogen out of this. It is more complicated than the regular find the empirical formula. But this part is the same. We're going to divide by the smallest. So this one's smaller. So that one's going to be 1. And this ends up being 2.5. So what do? Multiply by 2. So times 2 is 2, and times 2 is 5. So we've got C2H5. Any questions? These problems are tedious. There's so many steps. But all of these individual steps are skills that are really, really important to be successful in chemistry. Converting grams to moles, looking at a chemical formula and identifying the ratio of moles of element to compound. Those sorts of things are very important. Can you pass the class if you can't do a combustion analysis problem? Absolutely, you can pass the class. You could probably even get an A. It'll be on the test, but it's not going to be the whole test, okay? Calculating an empirical formula just from percentages or masses of elements, that is more important than this, okay? So if you're just like overwhelmed and you're like, I give you permission to skip the combustion analysis part. But the A students, anybody wanting to go to medical school or be a scientist, you should learn how to do this. Don't push that, push this. Okay, here's another one. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produces 1.600 grams CO2 and 0.6551 grams H₂O. Find the empirical formula of the compound. This is like the previous one, but worse. Because this one also has oxygen in it. We're going to start out the same. 1.6004 grams of CO2. I'm going to convert that to moles of CO2. And the molar mass of CO2 has not changed since the previous slide. And there's 1 mole of carbon per mole of CO2. So there's different ways to think about this. In this problem, I am going to need the mass of the carbon, but I'm also going to write down the moles because I'm going to need that as well. So that's moles of carbon. And I've got 0.6551 grams of water. So this is the same calculation. 1 mole of water divided by the molar mass of water. And then 2 moles of hydrogen per 1 mole of water. And you might be beginning to see why I insisted that you learn how to write stuff down. Because good luck doing this one in your head. There's just too much stuff going on here. 0.07272 is a cool number. 2 moles of hydrogen. Great. Got moles of carbon, moles of hydrogen. There's also oxygen. How do I figure that one out? I'm given the mass of the sample. I have to subtract the mass of the carbon and the mass of the hydrogen. The remainder is oxygen. I can't use these masses. This one's bigger than that. That's possible because it's combining with O2 that came from outside the compound. The O2 in the products here could possibly have come from the compound itself, but most likely it came from the oxygen gas that I was blowing in there. So I've got my moles of carbon and hydrogen, but I also have to calculate the mass of carbon and the mass of hydrogen so I can find the mass of the oxygen. I know, right? What? 12.01 grams per mole. Those are the masses of carbon and hydrogen. My sample was 0.8009 grams. 0.4367 grams of that was carbon. 0.0733 grams of that was hydrogen. What's left is the oxygen. And what do I have to do from grams of oxygen? I need moles of oxygen. So I've got this many moles of oxygen, and I've got this many moles of hydrogen, and this many moles of carbon. This is a hard problem. There's a lot of stuff going on here. And it's very easy to get in the middle of calculating stuff and forget what you were trying to do in the first place. You're like, okay, I calculated a number, now what do I, oh, wait a minute. I'm trying to find the empirical formula. I needed the moles of each element, and now I need the mole ratio, right? So I'm going to find the smallest of these. It's 0.01818. 18181. I'm going to change this to red, so maybe it stick out a little bit. So that one divided by itself is 1. This one divided by 4.03. .00. Phew, at least we don't have to multiply these. So I've got 2 and 4 and 1. C2 H₄O. Empirical formula. Yeah.
Do you mind explaining that bottom row? How you find the most
I don't mind explaining that at all. So this is something that happens a lot in science. There's something that you want to know, but you can't measure it directly. So you have to measure the other things and find it out indirectly. So we can measure the mass of carbon dioxide that's given off. And from that, we can find the moles of carbon or the grams of carbon, right? From the mass of water, we can find the mass of hydrogen. We need the mass of oxygen, but that's not something we can measure directly. But the law of conservation of mass says that mass is neither created nor destroyed. And so if this was the mass of the original sample, that's the mass of the carbon plus the hydrogen plus the oxygen. So when I know carbon and hydrogen and subtract those from the mass of the whole sample, that gives me the mass of the oxygen. Does that help? So we find the mass of the oxygen by difference. So this one here is my original sample. This is my mass of carbon from over here. And this is the mass of hydrogen from over there. The difference is the mass of oxygen. Anybody else?